Hello, welcome back to Intro to Cognitive Science. Here we are at the final week of classes, and we haven't gotten through everything we would like to. There is that I would like to. I'm sure you've had your fill, but it's an exceptional semester. So I'm going to just take these two lectures to introduce you to some ideas that will more or less skip across the surface of. We would normally spend more time on them, but I'll give you sort of the short versions of them. Things I want you to know before you leave, So this is the odds and ends series. This one's about neural networking. Now, we've touched on it before in various ways throughout the course. Today, we're going to get a little more specific and, as I like to do, run you through some interesting examples of real-world things that use this. So, neural networks. What are we talking about with these? Well, we can start with talking about a neuron. A normal neuron, like the ones in your head and your arms and everywhere in your body that helps you be you, it has various features. You don't need to memorize all these things, but it's a sort of a simple, simple in one sense. It is a biological entity, so it's very complex, of course, but you can think of it in a fairly simple way. It has dendrites that take information in from other cells. It detects if they are firing or not. It has its body where it sort of integrates the information, and then it sends it across its very long, spindly thing called an axon, where it can then send a signal to influence other neurons. So it will release a neurotransmitter, and the other neuron will pick it up and say, ooh, it's time to fire. That is the basic unit of your information processing, of your muscle movements, of everything that you do, everything your brain likes to do, is using neurons. We can simulate this. As I said just now, we can take a sort of a simplified version of this. I just gave you a simplified version of this. We can model that with math. We can make an artificial neuron. So artificial neurons, essentially, they attempt to capture the general behavior of a neuron by saying, okay, there are other neurons connected up to this neuron. My neuron's going to do some kind of summing. It's going to say, okay, these three neurons are active and this one's not. Based on how I weight those signals, I can use them positively or negatively. And then I will come up with a sum that if it crosses a particular threshold, I'll say, yes, I'll also send my information on. It's not exactly how a real biological neuron works, but I hope you see the parallels, right? It can take in information. It does some kind of fancy steps to integrate that information into a decision about whether or not it will fire and send the information onward, right? So that's the idea. This is the basic unit of any neural network, is something in this realm. There are variations on how you do this and to what degree you try to actually simulate more of neuron behavior or just become a more simplified version for some specific, programming task. But in general, this is the core idea of the artificial neuron. We can see how you might change some of the weights and the threshold to achieve different things. So if we think about some of the most basic processes, you can think about Boolean things like not. Okay, so what is not in the Boolean world? The not means whatever information is coming in, output the opposite, right? If it's a 0, output a 1. If it's a 1, output a 0. So in this case, the input coming in, we can multiply it by -1, according to the weight. The input coming in is at 1. Invert it. The weight setting on this particular connection. So the input is on the left here, and the output is what we result in. And in between, we have our artificial neuron, the threshold of which is just below 0, and the incoming weight of which is negative. So it's going to invert the signal. You don't have to really focus on this, but the idea is that you can set up the weights and the thresholds of an artificial neuron to do a calculation, a very small calculation, a Boolean calculation, a binary calculation. So that's the not perceptron. Here's an and perceptron. This one has two weights, and the idea is they both need to be active for this perceptron to make the decision to fire off. So again, we can capture that with the math of the weights. In this case, we just say, okay, the only way I'm going to fire off is if when I add together the two weights coming in, they add up to two or more, right? There are at least two active weights coming in. That math works, and we end up with a single perceptron that takes inputs from two other perceptrons and does an AND operation on them. And again, it's one of those very simple Boolean level calculations that you can do, and it works in this world. We can convert an AND perceptron to an OR perceptron by just lowering that threshold and saying, okay, well, as long as either of them is active, then I'll go ahead and fire. Threshold is a little lower. It's like floating around 1. So now if either of them is active, then we make the decision to fire. So we've just covered 3 extremely key Boolean operations that allow us to do all kinds of other complex things. So we could talk for a moment about the first step toward that, right? The very slightly more complex XOR operation. Who doggy? Okay, XOR. XOR just means I only want 1 or 0. So I only want one of these inputs to be active or the other input to be active. It's like the equivalent of saying, oh, I hate those two when they're together. I'll only go to the party if one of them is there and not the other one. They're such a pain in the butt when they're both there. But I won't know anybody if neither of them go, so that's a pretty delicate social balance, but I hope it illustrates the point. You don't want to, if you have that going on in your life, maybe rethink some of your friendships. But so this is a more complex operation than our nice nots, ands, and ors, but I won't walk through this one. The idea is that you can combine an and an or, and through some special inversion of the and specifically, you can achieve with 3 perceptrons this slightly more complicated operation. So the idea here is that this one simple idea that follows the pattern of a neuron, of how real neurons work, can be expanded to capture a more complex phenomenon. So, again, to recap, one node in these neurons, these artificial neurons, perceptrons, we could call them a node in a network, can take in information in the form of some activation level, just like a real neuron might, and it can output information according to its small local rules for how to do that. What are the weights of each input? What's the threshold at which I decide to fire? And output its own activation level further on in the network. So it simulates neurons in this very simple way, and which are in their own way also quite simple at the informational level, not at the biological level. But the real trick is not just that one of these things works, it's that we can follow the line of, from the most basic possible computations, next step is XOR, and then next step after that, keep going until you have very complex networks. This one's not even especially complex, but the idea is that if you just increase the bandwidth, right? Instead of taking a single Boolean value of an input and then outputting a single Boolean value, maybe take 10 Boolean values. Maybe take 1,000 Boolean values and output 1,000 Boolean values. And remember, those outputs, those inputs and outputs, can map to things like an image. Think back to Mar's early vision, right? Where Mar would propose the things like the zero crossings, right? So This is a way that we can take these basic units that are neurally inspired and have them produce very complex operations. Next, neural network learning. So, one of the cool things about neural networks is that they can be taught. So, in fact, that's one of the key things about neural networks. They don't just, we don't have to build them manually. We can, of course we can, but the really neat thing is that because the rules of an individual neuron are very simple, you can allow them to adjust their own rules slightly based on whether or not they're firing. So, there are two major categories of learning in neural networks. The first is supervised learning, where feedback is given to the network so it can know its own error. And then there's unsupervised learning, where there's no specific end case. It doesn't necessarily, there's no task it's being assigned. It's just as neurons fire next to each other, according to some input you throw at it, they will start to build their own associations. So let's talk about each of these in turn. Unsupervised learning. This is Hebbian learning. That's the name that you can see this labeled as. Neurons that fire together, wire together. That's one of those little like pocket maxims you can keep in your mind, in your belt, for a while. It's useful to know. So if one neuron fires because of something, because say something I saw, and another neuron fires because of that, they might develop an association together where one neuron firing will cause the one next to it to fire, or the one further down the chain to fire. They will build up a positive weight just by the nature of experiencing some stimulation at the same time. So the idea here is that those neurons that are physically near one another, this is the neurobiological reason that this should work, if they fire at the same time, it's good for them to just have a positive association. In fact, it's metabolically efficient for them to have a positive association. It makes it not as, we don't have to go through all the trouble of having them fire all on their own. They can just say, oh, that one fired, I'll go ahead and fire too, right? So the cool thing is that this doesn't require any feedback. It doesn't necessarily have to learn that, oh, I did something wrong. It can just build a network. And what might you use this for? Well, you can see this in things that are called pattern recognizers. So these, basically, you just show them loads and loads of images as input, and then the neurons that happen to be stimulated at the same time will start to build an association, so that eventually, if I show it a particular image, I can see if it activates properly, or if some part of the image is wrong and causes it to the cascade not to quite work. The connections won't work as well because the neurons have been trained together. So the idea is that I can show you the Bohemian waxwing, that not you, but the network. I can show the network the Bohemian waxwing 100 million times. See its face, right? See the upper left square of the part attention. And then I show the network a cedar waxwing. Now they're very close together. They would have a lot of things firing in common, but because the Bohemian waxwing network has been trained to pick up these little blushes you see in the top left image of the bird, the cedar waxwing does not have those color blushes, right? The colors on the cedar waxwing are more brown and white, whereas the Bohemian waxwing has more of this red hue to it. Because that red hue has been detected in the pattern over and over as the network was trained, when it's missing, it causes the pattern recognition to fail. So that the one that was trained on the Bohemian waxwing is not going to fire on the cedar waxwing, which is an important thing. The ability to distinguish things that seem ostensibly similar is very powerful, and that is one of the coolest parts of these kinds of training. Now, supervised learning you should also know about. This is the way of giving feedback to a network to say, hey, if I know what the answer should be, like I want this network to train to a specific output, and the network then fails to produce it, well, we have a discrepancy. What if we just give that back to the network? So we can give what's called an error signal to the network, and it can see how far off it was from the correct answer and start to adjust itself. Now, the basic idea is that the way it adjusts itself is it will change its own weights and say, I was very far off. I guessed 3 when it should have been 3 million. Maybe I will reduce my firing thresholds for whatever, right? I will adjust the incoming weights. Now, when you need to do this on a more complex network than a single node, you can use what's called backpropagation. And the idea is that you can propagate that error signal at the output end of your network, where your network is trying to do recognitions or whatever. And you can propagate it all the way back through the network, and you can sort of calculate a given neuron's responsibility for the error, right? So depending on what its weights are in the connection between one neuron and the next one, and so you can figure out what its contribution was to the wrong signal, and you can update its weights and thresholds a little more than you might one of the neurons that didn't fire, right? So that's the idea of backpropagation, giving a signal to the system to say, hey, you were way off, you should probably tweak some things. And so it sends it all the way back, and every one of the nodes updates itself and tries to figure things out. So one thing you should know about backpropagation is that there's not actually a lot of evidence that neurons can do this. Because how would that even work? A neurotransmitter is sent forward from the end of one neuron and is caught by the next one. The next neuron, there's no evidence that it sends information back to the previous neuron in any way whatsoever. So whether or not this is biologically plausible, not totally clear, but it is useful for at least the early days of neural networking. So let's look at some applications of neural networks, which are quite interesting. So first, I'm going to show you AlexNet from 2012. So this is it's unsupervised. It didn't require any sort of feedback. There was no explicit task. The goal of AlexNet was to create a large-scale image classification network. So the idea was they wanted to train it to be able to identify the category of various images. Things like dog, house, food, books, that kind of stuff. So the basic idea is that, or the basic process rather, was they would feed it thousands of dog-based images, right? Here's dogs, here's a bunch of dogs, here's houses, here's food, right? And then they would, by letting them just fire together and wire together, each layer of the network would start to exhibit the ability to distinguish certain things. And as the layers go up, they get more and more complex. So at the lowest level, it's like very basic edge detection, kind of like the stuff that we saw in Mars, zero crossings. And it would propagate up into things like patterns, and then, so not just, but like patterns like, what's the word? Like texture, right? Right there on my slide. Textures, so edges to textures to more complex shapes like a dog's snout or a book, until you get to the point where there are sets of neurons that are sort of most active when the trained when the network is seeing something that it was trained on, for like house. So let's look at this. This is the image of some of those features. Now, these are just abstract output images, but they help you get a sense of what kinds of things stimulate each layer the most. So at the very bottom, we see it's almost just like diagonals and slight waves and things like that. And then we get more into more complex substructures. Like in layer 3B, you see there's lots of like edges for things like books, right? There's circles for things like eyes. There's kind of these swirly patterns for things like fur blurring, right? I say blur or whatever, but like the swoosh of fur, right? So you might see that if you feed the network something that stimulates layer 4C in houses, you'd see that a lot of different connections are propagating up until you can tell that the network believes that this is a house. It's hard to make that connection. It's the idea of, based on the inputs from the bottom, propagate up the layers until you get to this really abstract layer that says, hey, I'm pretty sure that's a house. I will tell you that it's probably not a book or a dog. It's probably a house. It doesn't know. It doesn't have any way of training itself. But because each one of these layers has fired together and wired together over many, many, many instances of each of these kinds of photos, it's able to, using these kind of blurry, crazy looking images, again, these are just the outputs that stimulate them most, but these help you see how that layer might be able to recognize, oh, that's probably a house. Whereas a different image might stimulate a different set of neurons and show up to, oh, that's probably a dog. It doesn't have none of the features that activate my house neuron are activating right now. So it seems unlikely that this is a house. So, and you can see more. You can see restaurant dishes, kind of bushels of food. It looks like certain colors are most present in those. All of these things help. Palm trees on the left there, wheels, all the spokes and axes and axles and such. Also, some of them are fairly horrific, but that's the idea. So that is one of the kinds of tools you can use, you can build out of these neural networks, a pattern recognizer. Same idea, but in the opposite direction. I mean, it's used in both directions. If you can create one of these networks, you can typically reverse it in just a simple mathematical way. But this is a handwriting generation algorithm. It's based on the idea of doing the same kind of thing. You just train it using written words, but this time it's supervised. So you want it to be able to recognize words, but you also need it to output the correct words, right? So post offices use this all the time. The ability to take a quick snapshot of your crummy handwriting on your letter, and because it's been trained on millions of these kinds of photos of these kinds of handwritten text, and it has a pretty good, the post office it will figure out if it's sent the letter to the wrong place, right? So there are ways of allowing it to check in and get feedback. So you can train these systems, and let's get to the fun part. Sorry. So cogito ergo sum, carpe diem, other Latin nonsense is something I input into this system, and it just dumped right out 5 lines of handwritten text. You can see it's a little bit messy in places. Sometimes it misses a dot in the I. Sometimes it doesn't quite finish letters. But look at these different flavors. These look like 5 different people wrote this. Maybe the bottom 2 are pretty close for a minute. Then one of them gets more fancy than the other. That's the same idea. It's the same idea as the image capturing. The idea is that this is a way of and it cuts both directions, right? I could feed it in the reverse direction. I could feed it one of these photos of handwriting, and it would be able to pull out cogito ergo sum, carpe diem, other Latin nonsense. So that's the idea. Just another interesting application. Something else you should hear of is generative adversarial networks. This is a pretty cool way to leverage the fact that networks are pretty good at these kinds of both input and output, and you can pit them against each other. So this is the best the allegory for, or what's the word? Analogy? Yeah. For how these work. There are two networks. One is a forgery artist trying to produce the most realistic image possible, and the other is a detective trying to outsmart the forgery artist and detect the false images. You can see how they're kind of both trained on different things a little bit, but the idea is that because one of them can produce an output that the other can take as input and then give back feedback about, hey, I think you're wrong, hey, I think you're right, then it becomes this idea of, so the generator can create an image and the discriminator will attempt to identify it as either real or fake. So the generator gets rewarded for fooling the discriminator. So for creating an image that is passable, it gets positive feedback. The discriminator is rewarded for spotting the fakes, right? So they both have ways of getting positive feedback, and they both have ways of getting negative feedback. So they can train themselves and each other, right? So it's competition. Let's look at some of the outputs of a long-term generated, a generative adversarial network. Just take a second and look at some of these. They're pretty good. But after some inspection, you start to notice some things that aren't so great. The wolf has some weird legs. The bubble's pretty good. The cup, there doesn't look like there's actually a plate there. The mushroom has a lot of eyeballs all over it, which is not the greatest. The fountain, there's some weird stuff going on with the physics of the water, but at first blush, you were fooled, right? Not forever. You don't have to cop to that, but these look good. But then you see that the rocket ship looks kind of like lipstick, I guess, right? It got so many of the details right, and at this really broad level. Okay, let's look at another. Let's do a little exercise. Which one of these faces is faked by a generative adversarial network? It's both. It's tough to tell. You can pick up some of it from the eyes. You can see on the guy there's some kind of funniness around the hair. On the gal, there's this. She got a really long canine tooth going in a not a great direction. Her ear is kind of chopped up, but dang, are these pretty good, right? It's tough to tell right off the bat. It takes a lot of effort to figure it out. So that's some of the ways that you can at least see how powerful these networks can become if you allow them to train. Now, let's talk science. Are these plausible? Rumelhart and McClelland. Let's talk about language a little bit. Learning past tense in English is really weird. Think about so many of our words have this wonderful, solid structure of just adding ed to the end. Baked, walked, danced. But there's so many weird ones. Gave, not gived, went, not goed, fought, not fighted, right? Children screw this up all the time. They exhibit what's called over-regularization. So, the question is, can you build a network that will create those same kinds of errors? As in, can the network's learning match or at least simulate the same kind of learning that children go through? Is this a neurological process, and can it be modeled with artificial neurons? So, they came up with two ideas. Regular and irregular verbs are the two categories, and the idea is that It would learn the regular patterns and then learn the irregular exceptions. At first glance, you might think that this seems like, oh, that's probably a physical symbol system thing, right? You could just have it learn the regular route to applying ed to the end of a verb, and then, have a list of alternatives that would stop it. But the question is, do you actually need to go as far as explicitly representing those rules? Would you say that most of us actually know all the rules and have like these stop lists, or are we doing something a little bit more fine-grained and massively distributed and weird, right? So the physical symbol system version of this might look like this, right? Verb stem comes in, some kind of operation happens that combines a list of exceptions as well as the regular route of just adding ed, and then the exceptions will somehow block and stop the ed version from happening, right? The question is, can a neural network do this and with less explicit structuring, right? This is a very specific kind of structure, a little bit more than you might expect from a kid, right? So the question is, can a neural network being trained on these things achieve this? Rumelhart and McClellan's neural network attempts to do it this way, without any explicitly teaching of rules. The idea is that they have, actually it's multiple neural networks. You don't have to know all these things. The idea is you would input the phonemes, right? The actual like sounds of language as distinct possible options. And they would have these two middle networks that do this thing called Wickel features. Just like it converts these phonemes into these sort of deconstructed structures. You don't have to worry about it. It's reduced root representation of the word, and then a reduced root past tense representation, and then they get plopped back out as phonemes again. So essentially, the phonemes get broken down. The way that the words sound gets broken down into these sort of, sub informational features that can be passed between these networks. Yada yada. The output is again phonemes. So the idea is if you say, hey network, what's the past tense of bake? And then it would do its thing, propagate, and it would output baked, right? What's the tense of go? It would do its process and it would output went, right? So, and it was trained on these very frequent verbs, so it's not a big mess. I just explained that on the wrong slide, I think. So check this. The phonemes come in on the left. They are the way the word sounds. They get chopped up into these little Wickel features. That just means little feature in German, which is like just a more abstract data type representation. And then the connections between all these things produce the correct output. Notice there's no specific area where we say, oh no, there's irregular verbs in there. Oh no, there's regular verbs. There's no categorization. There's no coding that in. And then the idea is that if you do this training and you allow them to learn and to train, like, they give them an error signal, what does it do? Does it actually simulate that process of learning? Does it make hyperregularization errors? First of all, can it do it? Can it distinguish between irregular and regular verbs and get the proper past tense letters? And then does it also, if it can distinguish them, does it make the overregularization error first? Does it start by doing the wrong thing just like kids do? And I'll tell you the answer is yes. The irregular correct words grew more slowly. The regular words were adapted very quickly by this neural network setup, and the irregular ones grew a little more slowly. It was harder, right? There were more of them. There were more categories for it to have to learn through. It didn't do it in the literal time frame, the same time frame. It's just hundreds of trials and stuff like that. It's not exactly how humans do it, but it follows the same pattern, which is exciting, right? We're seeing neural networks being used for something that seems to mirror the way that humans do things, or at least the way that we expect humans to be able to do things. So ultimately, the question is, we don't know if the kids actually know the rules, but this is a nice neural, very little overt structure going on here to produce something fairly human. Now we can talk about another network that was built to capture another phenomenon in humans, object permanence, which is really just another way of saying memory. So, Munakata's neural model of object permanence. The basic challenge was, when an object is no longer present, what does the network do with that? If there's no input, there can't be any activation, right? We sort of, from what we've seen so far, we just think, okay, there's inputs, a bunch of things happen, and there's outputs. If I'm in a room and you go walk behind a wall in front of me, I know you're there, right? I don't think that you've died. I don't think that you've vanished. I know you're there. But a neural network, the way we're used to looking at them, doesn't have a way of keeping track of you. All we have is this external stimulus. Oh, you're no longer in my vision. You must be dead, right? So the idea that is introduced is the idea of recurrent neural networks that have connections unto themselves. A recurrent neural network is able to feed back information in its middle layers to earlier layers to say, hey, this is probably still here. This is probably still here. Allowing a signal that might be very useful, like, oh, my dad's not dead. He just walked behind a wall, right? So being able to keep this object permanence, right? The middle layers allow this signal to persist. So let's look at a network that would kind of simulate this, and you can maybe see a little more clearly how this would work. So on the top there, we have a box is sliding over a circle, right? Early on, we have two little networks. One is keeping track of the location of the circle on the top row. So you see the squares on the top row in that second area. And then the bottom row has its own squares, right? And you can see the bottom row is tracking the location of the square. It moves over, it moves over, it moves over, it moves over, left to right. And eventually, it occludes the black circle. And so now, the representation of that top layer says, oh, there's nothing there anymore. I don't know where the circle is. So that's the idea. The top row is showing the circle, the ball, and the bottom row is showing that barrier, the square. So the question is, how can you set the system up so that the ball will persist during those middle steps? Recurrence. So you have this additional layer on the side that it sort of keeps information active. And it allows, so, okay, I saw something here before. I'm going to hang on to this information and feed it back so that the next time we do a process, the next time we process this situation, I have memory of what happened. So you see here, the input can send information up into these recurrent network and then send it back down to the input for future iterations. Again, you don't have to memorize exactly how all this works. The point is that by reconnecting a network to itself, we give it a sense of memory. That's true of computers. That's true of you, the human. So that's Munakata's neural model of object permanence. The idea is that recurrent connections give the network a form of memory, which is pretty important, right? If information couldn't persist, there would be so many things that would be completely impossible. But when you allow information to persist and hang on for multiple steps and stick around for future use, even if you're not looking at something anymore, then that's super critical, right? That ties the current situation, the current moment, the current slice of time to the future and the past. So we're getting a little philosophical here, but that's the nature of this. By having a recurrent network, you enable it to exist in time, not just space. So that's our little skipping across the pond of neural networking. It's the idea that, if you have one big takeaway, a large number of small individual nodes with fairly simple rules can be combined together to create something much more intricate and complex. Emergence is the key idea there. And the complexity emerges from interactions of simple agents. And we've shown that these can rival humans, they can exceed them in some places, and sometimes they can really show us some things about ourselves. So that's it for this this preview / recap somehow. And so the final thought. What's another phenomenon in this world that captures this idea of emergence? What complex process can you break down and see fairly simple rules guiding various individual separate components? All right, that's it. Take care.